Imagine flying at 35,000 feet, where the air outside can be colder than minus 60 degrees Celsius. Yet a massive airliner cruises normally through the sky, carrying hundreds of passengers. So why doesn't the aircraft freeze? Subscribe, because we're going inside this incredible machine to uncover how it survives the extreme cold. The airplane doesn't survive the cold simply because its outer skin is strong. Its entire design works together to manage temperature. The engines generate enormous heat. Specialized systems move and control that heat, while insulation protects the cabin and critical equipment. Even when the outside air reaches minus 60 degrees, the aircraft keeps its internal environment under control. At cruising altitude, the temperature can fall far below what we experience on the ground. Around 35,000 feet, the air is much thinner and extremely cold. But that doesn't mean the entire airplane instantly reaches the same temperature. To understand why, we first need to see what the atmosphere is doing around the aircraft. Here's the important part. The outside air may be extremely cold, but the aircraft is constantly receiving and producing heat. Sunlight warms its surfaces, electrical equipment generates heat, and the engines create enormous amounts of thermal energy. The airplane systems continuously balance these heat sources against the freezing environment outside. The biggest source of heat on an airliner is its jet engine. Air enters the front at high speed. Then the compressor squeezes it to extremely high pressure. Inside the engine, fuel burns with this compressed air, creating temperatures far beyond anything outside the aircraft. That intense heat becomes a powerful advantage in the freezing sky. But the engine's heat isn't only used to create thrust. Some of the hot, compressed air produced inside the engine can be tapped and routed into aircraft systems. This principle, known as engine bleed air, has played a major role in traditional aircraft environmental and anti-ice systems, helping the airplane manage the extreme cold outside. Inside a traditional jet aircraft, carefully controlled hot air can be taken from the engine's compressor. It is then sent through a network of ducts towards systems that need heat. This gives engineers a powerful source of thermal energy without adding a separate heater large enough to warm the entire aircraft. The air coming from the engine is far too hot to enter the cabin directly. It first passes through valves, heat exchangers, and temperature control systems that reduce and regulate its temperature. Only after this conditioning does the air become suitable for the cabin environment, turning intense engine heat into something passengers can safely use. The same process helps keep passengers comfortable. In many traditional airliners, conditioned air from the environmental control system is mixed and regulated before entering the cabin. The aircraft doesn't need to make the entire cabin warm from scratch. Instead, it continuously controls the temperature and airflow while fresh air is supplied throughout the flight. But heating the air is only part of the solution. The fuselage itself acts like a thermal barrier. Multiple layers of structure, insulation, interior panels, and controlled airflow reduce the transfer of heat between the comfortable cabin and the freezing air outside. The aircraft's outer skin is exposed directly to the freezing air, but cold itself doesn't automatically create a thick layer of ice. At cruising altitude, the air is usually very dry, and there may be little liquid water available to freeze onto the surface. The bigger icing threat appears when an aircraft flies through clouds containing supercooled water droplets. When an aircraft enters a cloud containing supercooled droplets, the situation changes quickly. These tiny liquid droplets can remain unfrozen below 0 degrees Celsius, but when they strike a cold wing or engine surface, they can freeze. That's why aircraft have specialized anti-ice systems designed to protect the areas where ice could seriously affect performance. The wing's leading edge is one of the most important areas to protect from ice. Even a relatively small buildup can change the shape of the airflow over the wing. That can reduce lift and increase drag. So when icing conditions are detected or expected, the aircraft uses specially designed systems to keep critical surfaces clear. The engines need protection too. Ice forming around the engine inlet can disturb airflow and create serious problems for the engine. In many conventional jetliners, heated air from the engine is routed through protected areas around the inlet. This keeps critical surfaces warm enough to prevent dangerous ice buildup during flight. At first, the freezing sky seems like the biggest threat. But the real danger is often liquid water inside clouds. These droplets can stay liquid even below 0 degrees. When they hit a cold aircraft surface, they can suddenly freeze. This is called supercooled icing, and it is one of the key reasons aircraft need anti-ice protection. Ice is dangerous because an aircraft wing is carefully shaped to control airflow. A rough layer of ice changes that shape and disturbs the smooth flow of air. The result can be less lift and more drag. That's why engineers focus so heavily on keeping the wing's leading edge clean whenever the aircraft encounters icing conditions. The aircraft doesn't wait for a thick layer of ice to build up. In many jetliners, hot air from the engine is directed through passages near the wing's leading edge. That heat keeps the surface above the temperature where dangerous ice can form. The result is a wing that can continue producing smooth, predictable airflow in icing conditions. The same principle protects the engine inlet. If ice builds up around the inlet, it can disturb the airflow entering the engine. So controlled hot air is routed through the inlet's anti-ice passages, keeping this critical surface warm. It is a simple idea with a powerful result, using the engine's own heat to protect the engine. At the front of the aircraft, the windshield faces the freezing airflow directly, yet pilots still need a clear view through it. Aircraft windshields use multiple layers of specially engineered glass and transparent materials, along with heating systems that help prevent dangerous ice from forming on the outer surface. The windshield heating system works like a carefully controlled electrical heater built into the transparent structure. Electrical power warms the designated layers, keeping the outer surface within a safe temperature range. This prevents ice from building up while also helping manage the extreme temperature difference between the warm cabin and the freezing air outside. Jet fuel also faces the extreme cold. But it is not ordinary gasoline, and it is specifically formulated for aviation. Jet A and Jet A-1 have low freezing points, with Jet A-1 freezing around -47 degrees Celsius. Yet at high altitude, fuel temperature can become very low, so engineers carefully manage fuel quantity, tank location, and heat transfer. The fuel system has another important role: heat management. In some aircraft, relatively warm engine oil or other fluids can transfer heat to colder fuel through dedicated heat exchangers. This helps cool the engine systems while also preventing the fuel from becoming excessively cold. The airplane is constantly moving heat around instead of simply losing it. Deep inside an airliner, hydraulic systems provide the force needed to move major flight controls, landing gear, brakes, and other components. But hydraulic fluid must keep flowing even when the aircraft is surrounded by freezing air. That's why the system uses specially selected fluids, controlled temperatures, and carefully designed components. Cold temperatures can make fluids more resistant to flow, so engineers cannot simply ignore temperature. Hydraulic systems are designed with suitable fluid specifications, insulated or protected components, and heat generated during normal operation. The goal is simple: keep the fluid within its required operating range so the aircraft's controls remain responsive. Modern airliners depend on thousands of electrical components, from navigation computers to communication systems and flight control equipment. At cruising altitude, these systems are surrounded by extremely cold air. But most critical electronics are installed inside protected areas, where temperature, airflow, and electrical power are carefully controlled. Electronics don't just have to survive the cold. They also have to get rid of the heat they generate. Avionics systems continuously produce thermal energy, so aircraft designers provide controlled cooling and airflow. The challenge is maintaining the right temperature range, cold enough outside for flight, but stable enough inside for sensitive electronics. An aircraft doesn't just create heat and throw it away. Heat is constantly moving between different systems. Engine oil, electrical equipment, cabin air, hydraulic systems, and fuel can all exchange thermal energy. Engineers carefully control these transfers so one component doesn't become too hot while another becomes dangerously cold. Think of the airplane as a carefully balanced thermal network. Some components constantly produce heat, while others need to release it. Engineers connect these systems through ducts, heat exchangers, cooling airflow, and insulation. The goal isn't to make everything hot. It's to keep every critical component inside the temperature range where it can work safely. At cruising altitude, the fuselage separates two completely different environments. Outside, the air can be colder than -60 degrees Celsius. Inside, passengers need a stable and comfortable temperature. Between them are layers of structure, insulation, and interior panels that slow down heat transfer and help protect the cabin from the freezing air. Insulation alone cannot keep an aircraft warm forever. It only slows the movement of heat. The real protection comes from combining insulation with continuous cabin heating, controlled airflow, and heat generated by the aircraft's systems. Together, these layers create a stable environment inside while the airplane races through freezing air outside. As the airplane begins its descent, the outside temperature gradually becomes warmer. The aircraft can move from an environment near -60 degrees Celsius toward much milder air in a relatively short time. But this change doesn't suddenly shock the airplane. Its systems and structure are designed to handle large changes in temperature and pressure throughout every flight. An aircraft's materials expand and contract slightly as temperatures change. Engineers account for these movements when designing the fuselage, wings, joints, and other structures. The goal isn't to prevent every temperature change. It's to make sure the aircraft can safely absorb those changes thousands of times during its operational life. So now the mystery becomes clearer. An airplane at -60 degrees isn't simply sitting in the cold. Its engines are producing enormous heat, its systems are constantly moving and controlling that energy, and its insulation slows heat loss. Meanwhile, anti-ice systems protect the surfaces where freezing water could become dangerous. The secret isn't one magical material or a single heating system. It's thousands of engineering decisions working together. From the engine and fuel system to insulation, electronics, hydraulics, and anti-ice protection, every part is designed around the same challenge: keeping the aircraft reliable while the outside world reaches temperatures far below freezing. The answer is not that the airplane somehow stays warm by itself. It is a carefully engineered thermal system. Engine heat, electrical power, insulation, airflow, anti-ice protection, and specialized fluids all work together. Even when the outside temperature drops toward -60 degrees, the aircraft keeps its critical systems inside their required operating ranges. And that's why a passenger airplane can cross oceans thousands of feet above the ground while the air outside is brutally cold. It isn't defeating physics. It is using physics. Heat is generated, transferred, controlled, and released exactly where engineers need it. The next time you look up at a cruising airplane, remember, beneath that smooth exterior is a machine constantly managing an extreme environment. Even after all these systems are working, pilots and aircraft can still encounter serious icing conditions. That's why modern airliners continuously monitor temperature, airspeed, engine performance, and other flight data. Crews can also activate anti-ice systems when conditions require them, keeping the aircraft prepared for changing weather. A commercial aircraft doesn't face extreme cold just once. During its service life, it can experience thousands of flights, repeated climbs and descents, changing weather, and countless temperature cycles. Every major system is designed with this repeated stress in mind. Reliability comes from engineering for the extreme, and then testing those designs again and again. So, why doesn't an airplane freeze at -60 degrees? Because almost every part of the aircraft is designed around temperature control. Engine heat, anti-ice systems, insulation, airflow, fuel management, and protected electronics all work together. What looks like a simple flight through cold air is actually a carefully controlled battle against the environment. The next time you see an airplane disappearing into the clouds, remember what is happening beyond what your eyes can see. At temperatures far below freezing, thousands of systems are working together to keep the aircraft flying safely. If you enjoyed uncovering this hidden engineering, subscribe for more incredible machines and the science behind them.